Deep space. Stars scattered against absolute darkness. Look at this. What are you seeing? Most people would say darkness. Empty space. Nothing. But that answer is wrong. Space is not empty. It has never been empty. And the reason why reveals something deeply unsettling about the nature of reality itself. This is not poetry. This is not metaphor. This is physics. Experimental physics. The evidence has been mounting for over a century. Experiments have confirmed it. Mathematics demands it. Observations support it. The vacuum of space is not vacant. What we're about to explore will change how you see the universe. It will change how you think about existence itself, because the space between stars, between galaxies, between atoms, between particles is not what you think it is. Title card: Why Space Isn't Empty. Part 1. The ancient problem of nothingness. For most of human history, we believed in emptiness. The concept seems simple, obvious even, self-evident. Remove all matter from a region. Remove all air, all particles, all substance, all energy. What remains? Nothing. But this simple answer conceals profound difficulties. Difficulties that troubled philosophers for millennia. Difficulties that eventually forced us to rewrite our understanding of reality. The ancient Greeks debated this question endlessly. They called it the void. They argued about whether it could exist. Parmenides said no. He argued that non-being cannot be. That nothingness is literally inconceivable. Leucippus and Democritus said yes. They needed the void for their atomic theory, atoms moving through emptiness. Aristotle sided with Parmenides, but for different reasons. He claimed nature abhors a vacuum, that the universe fundamentally cannot allow it. That empty space would be filled immediately. He had elaborate arguments. Physics based on his theory of the four elements. Logic based on his metaphysics. He was wrong about the mechanism. Wrong about the reasoning, wrong about nearly every detail. But he was right to be suspicious of emptiness. The debate continued through the medieval period. The scholastics inherited the problem. They debated it in their monasteries and universities. Can God create a vacuum? Can God create absolute nothing? The question became theological, metaphysical, tied arguments about divine omnipotence. But underneath, it remained a question about physical reality, about what actually exists in the spaces between things. By the 1600s, we had better tools. Robert Boyle and Otto von Guericke built vacuum pumps. They evacuated air from sealed chambers, created regions with extremely low pressure. The closest thing to emptiness ever achieved on Earth. The experiments were crude by modern standards. The vacuums were imperfect, but they worked well enough to demonstrate something important. You could remove most of the air. You could create a space with near zero atmospheric pressure. And yet something strange happened. Light still passed through the evacuated chamber without any apparent difficulty. Sound did not. Sound requires a medium, air or water or solid material. But light moved through the vacuum as if nothing had changed, as if there was still something there to carry it. This created a deep problem, a problem that would take centuries to resolve. By the 1700s, Isaac Newton had given us a new picture of the universe. Space as a vast three-dimensional container, an infinite Euclidean stage on which the cosmic drama unfolds. Objects moved through it. Forces acted across it. Gravity reached across millions of miles of apparently empty space, holding planets in their orbits, governing the motion of moons and comets. But space itself did nothing. It was just there. Empty, passive, inert, a background. A stage, waiting for matter to fill it. This seemed reasonable at the time. After all, if you remove all the air from a chamber, what's left? Nothing, we assumed. We called it a vacuum. We thought we understood it. We thought the question was settled. But we were wrong. We were looking at the wrong thing. We were asking the wrong questions. We were about to discover that our deepest intuitions about emptiness were completely mistaken. The problem began with light. Light moves through space. We've known this since ancient times. Sunlight reaches Earth across 93 million miles of apparent emptiness. Starlight reaches us from distances that beggar the imagination, light years, millions of light years, billions, but light is a wave. By the early 1800s, we knew this with certainty. Thomas Young performed his famous double-slit experiment in 1801. Light passing through two narrow slits created an interference pattern. Bright and dark bands, proof of wave behavior. This was confirmed again and again. Light exhibits interference, diffraction, polarization, all the characteristic behaviors of waves. There was no question light was a wave. And every wave we had ever encountered needed something to wave in. Sound waves need air, or water, or some material medium to carry the compression and rarefaction. Water waves need water. The surface deforms, crests and troughs propagate. Seismic waves need the earth itself. The rock deforms. The wave travels through solid matter. Waves on a rope need the rope. The string oscillates, the wave moves along it. No wave could exist without a medium to support it. This was not conjecture, this was observed fact, universal law. So, what was light waving in? What medium carried light waves across the emptiness of space? Scientists of the 19th century proposed an answer. They called it the luminiferous ether. The word itself reveals the confusion. Luminiferous means light-bearing, light-carrying, space. They said, must be filled with this invisible substance, this ethereal medium that pervades all of reality. Light ripples through it the way sound ripples through air. But the ether needed to have impossible properties. Consider what was required. First, it had to be everywhere. In the space between Earth and Sun, between stars. Between galaxies, between atoms, filling every cubic centimeter of the universe. Second, it had to be perfectly transparent, perfectly invisible to all our instruments and senses. We can see through it without any obstruction whatsoever. Telescopes peer through billions of light years of ether without the slightest dimming or distortion. Third, it had to offer essentially zero resistance to motion. Planets orbit the sun for billions of years without slowing down. If the ether resisted motion, even slightly, the effects would be obvious. Planets would gradually spiral inward, their orbits would decay. Fourth, and most problematically, it had to be incredibly rigid. Extraordinarily stiff. Light moves at 300,000 kilometers per second, nearly 700 million miles per hour. For a wave to move that fast through a medium, that medium must have enormous stiffness. Far greater than steel, far greater than diamond. So the ether had to be rigid enough to support light waves moving at incredible speed, but also fluid enough, tenuous enough, to offer no resistance to planets moving through it, invisible but ubiquitous, substantial but undetectable, rigid but immaterial. These properties were contradictory. They violated everything we knew about materials and mechanics, about how substances behave, but the mathematics of waves seemed to demand them. Light was a wave. Waves needed a medium. Therefore, a medium must exist. The logic appeared airtight, the reasoning seemed sound. And so the ether hypothesis dominated physics for decades. It was taught in universities, assumed in calculations, treated as established fact. In 1887, two American physicists decided to test this hypothesis directly. Their names were Albert Michelson and Edward Morley, and their experiment changed everything. Albert Michelson and Edward Morley built an extraordinarily sensitive instrument, an interferometer. A device that could split a beam of light, send the two halves in perpendicular directions, then recombine them to create an interference pattern. The principle was elegant. If the two beams traveled through different conditions, they would return slightly out of sync, out of phase, creating visible interference fringes. Bright and dark bands, the pattern would reveal the difference in conditions. Here was their reasoning: Earth is moving through space, orbiting the Sun at 30 kilometers per second. The solar system itself is moving through the Milky Way galaxy. The galaxy is moving through space. If space is filled with ether, then Earth is moving through the ether, like a ship moving through water, like a plane moving through air. This motion creates an ether wind, a relative motion between Earth and the medium of light. Light traveling in the direction of Earth's motion would be moving with the ether wind. Like a swimmer moving with a current, light traveling perpendicular to Earth's motion would be moving across the wind, like a swimmer moving perpendicular to a current. The speeds would be different, the travel times would be different. The interferometer was sensitive enough to detect this difference, sensitive enough to measure the ether wind, to finally prove once and for all that the medium of light actually existed. They ran the experiment carefully, meticulously, with every conceivable precaution. They found nothing. No speed difference, no ether wind, no interference pattern indicating motion through a medium. Light traveled at the same speed in all directions. Exactly the same speed, to within the precision of their measurements. This was shocking, completely unexpected. The result made no sense within the framework of 19th century physics. They repeated the experiment, changed the orientation of the apparatus, rotated it to align with different directions, waited for different times of day when Earth's rotation would change the relative direction of motion, waited for different times of year when Earth's orbital motion would be in different directions relative to the distant stars. Always the same result: nothing, no ether wind, no detection of any medium whatsoever. The experiment was repeated by others, different locations, different apparatus designs, different years. Michelson himself repeated it years later with better equipment. Always the same null result: no ether wind. No variation in the speed of light. The ether did not exist. Or if it did, it had properties so bizarre, so paradoxical, so disconnected from ordinary matter that it might as well not exist. This should have been a crisis for physics. The foundation had been pulled out from under the theory of light. If there was no medium, how could light be a wave? What was waving? Some physicists proposed modifications to the ether hypothesis. Maybe Earth drags the ether along with it. Maybe the ether is contracted near massive objects. These proposals became increasingly contrived, increasingly ad hoc. The real answer would not come from modifying the ether hypothesis. It would come from a completely different direction, from a set of equations that unified electricity and magnetism. From the work of James Clerk Maxwell, 1865. James Clerk Maxwell publishes a paper titled A Dynamical Theory of the Electromagnetic Field. In it, he presents for equations, for mathematical statements that describe how electric and magnetic fields behave. These equations unified electricity and magnetism into a single framework, showed they were to aspects of the same phenomenon. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. But the equations revealed something else, something unexpected, something profound. They predicted the existence of electromagnetic waves, disturbances in the electromagnetic field that propagate through space at a specific speed. Maxwell calculated that speed from the equations, from fundamental constants that had been measured in laboratory experiments with electricity and magnetism. The speed came out to be approximately 300,000 kilometers per second. The same speed as light. This could not be a coincidence. Maxwell realized immediately what it meant. Light was an electromagnetic wave, not a vibration of some mechanical medium, not a disturbance in the ether, but a wave of the electromagnetic field itself. This was radical, revolutionary. It changed our understanding of light completely. But it also raised a profound question: what is a field? Think about it this way. You're holding a magnet, you move it near a paper clip. The paper clip moves, jumps toward the magnet. Something reached across that space, something exerted force across the gap. What was it? We call it a field, the magnetic field of the magnet. But what does that mean? What is the field made of? The field is not made of matter. It's not made of atoms or molecules or any conventional substance. It's not a fluid, it's not a gas, it's not a solid. The field is a fundamental entity in its own right, a new kind of physical reality. It exists at every point in space. At each point, it has a value, a magnitude, a direction, you can measure it. Place a compass at different locations, the needle points in different directions. That's the magnetic field at those locations, you can calculate with it. Use Maxwell's equations to predict how the field will change over time, how it will respond to moving charges, and when the field's value changes, things happen. Charges experience forces, energy flows, work is done. Maxwell's equations describe two fields: the electric field and the magnetic field. These fields are linked, changing one creates the other. They can oscillate together, create ripples, form waves that propagate through space. And those waves were light, visible light, but also invisible electromagnetic radiation. Radio waves, infrared, ultraviolet, all of it was electromagnetic waves. Disturbances in the electromagnetic field, this resolved the paradox. Light didn't need a mechanical medium like the ether. The electromagnetic field was the medium. But more than that, the field wasn't in space. It wasn't a property of space. It was occupying space, filling it, defining it. Space was not a passive container anymore. It was a field configuration. A structure with properties. This changed everything. But we didn't fully appreciate it at the time. That realization would take several more decades, and it would come from quantum mechanics. In the early 1900s, quantum mechanics emerged, a completely new framework for understanding matter and energy at the smallest scales. It revealed that matter has wave properties, that energy comes in discrete packets called quanta, that the act of measurement affects what is measured. The theory was strange, counterintuitive. It violated our everyday intuitions about how reality works. But it was also extraordinarily successful. It explained atomic spectra, chemical bonds, the behavior of electrons in atoms. It was tested and retested, always confirmed. By the 1920s, physicists began to apply quantum mechanics to fields, to the electromagnetic field, to other fields. This led to quantum field theory, a framework that combines quantum mechanics with the concept of fields. And quantum field theory revealed something profound, something that changes our entire picture of what exists. Particles are not fundamental. Fields are fundamental. Let me say that again. Particles are not the basic constituents of reality. Fields are. What we call an electron is not a tiny ball of matter moving through space. An electron is a localized excitation in the electron field. A quantum, a ripple, a disturbance in the field. What we call a photon is not a particle of light traveling through emptiness. A photon is a quantum of the electromagnetic field. An excitation, a discrete packet of electromagnetic energy. And here's the critical point. The field is always there, always present. Even when there are no particles, even when nothing seems to be happening, the field exists. Every point in space is permeated by fields. The electromagnetic field, the electron field, the quark fields. Multiple types of quark fields, neutrino fields. Multiple types of neutrino fields, the Higgs field, gravitational field. All the fields described by the standard model of particle physics, dozens of quantum fields, all stacked on top of each other, all extending through every point in the universe, all present, all real, all contributing to what exists. These fields are reality. They are not optional extras. They are not additions to space. They are what space is when you describe it correctly. They are never turned off, never absent, never truly empty. So when you look at empty space, you're not looking at nothing. You're looking at dozens of quantum fields in their lowest energy state. Still there, still present, still real, still capable of physical effects. Part 6, the quantum vacuum. Let's talk about energy. Everything has energy. Motion is energy. Heat is energy. Electromagnetic radiation carries energy. Even mass is energy, as Einstein showed. In classical physics, you could in principle remove all energy from a system, cool it to absolute zero. Remove all motion, all vibration, all activity. You'd have a system with zero energy, perfect stillness, complete inactivity. But quantum mechanics doesn't allow this. There's a principle, a fundamental law. One of the foundational rules of quantum physics, the Heisenberg uncertainty principle. The uncertainty principle is often misunderstood. People think it's about measurement, about the limitations of our instruments, about what we can know, but it's not. It's more fundamental than that. It's about what can exist. The principle states that certain pairs of properties cannot both be precisely defined at the same time. Position and momentum, energy and time, pairs of conjugate variables in the mathematical language. The more precisely one property is defined, the less precisely the other can be defined. This is not a limitation of measurement technology. It's a limitation built into the structure of reality itself. Now apply this to a quantum field. Consider the electromagnetic field at a single point in space. If the field had exactly zero energy and exactly zero fluctuation, you would know both its value and its rate of change with perfect precision. Both its position in field space and its momentum in field space would be perfectly defined. The uncertainty principle forbids this. There must always be some irreducible uncertainty, some minimum amount of fluctuation. Some energy that cannot be removed. This fluctuation is real. It's not a measurement problem. It's not ignorance on our part. It's not a theoretical approximation that will be improved by better theories. It's a statement about what exists, about what must exist. Even in the ground state, even in the lowest possible energy configuration, quantum fields are never completely still. They fluctuate randomly, constantly. At every point in space, these are called quantum fluctuations, or sometimes zero-point fluctuations, zero-point energy, because they exist even at zero temperature, even when you've removed every particle, every photon, every excitation you can possibly remove, even when you've cooled the system to absolute zero. Even when there's nothing there in the classical sense, the fluctuations remain. You might think this is theoretical, abstract, mathematical formalism with no physical meaning, but it's not. These fluctuations cause measurable effects, real effects. Effects that have been confirmed by experiments. Let me give you two examples. Two pieces of evidence that the quantum vacuum is real and has physical consequences. The first piece of evidence is called the Casimir effect. It's named after Dutch physicist Hendrik Casimir, who predicted it in 1948. Here's the setup. Take two metal plates, make them very flat, very smooth, highly polished, parallel surfaces. Place them parallel to each other in a vacuum chamber, very close together, micrometers apart, a few millionths of a meter. What happens? The plates attract each other, not because of gravity. The gravitational force is far too weak, not because of electrostatic charge. The plates are electrically neutral, no net charge. Not because of residual air pressure. The experiment is done in high vacuum. The force comes from the vacuum itself, from the quantum fluctuations of the electromagnetic field. Here's why the quantum fluctuations of the electromagnetic field exist at all possible wavelengths. All possible frequencies, from radio waves to visible light to X-rays to gamma rays. A continuous spectrum of fluctuations outside the plates in the free space on either side. All these wavelengths can exist. All these fluctuations contribute to the vacuum energy. Between the plates, only certain wavelengths can fit. Only fluctuations with wavelengths small enough to fit in the narrow gap. Longer wavelengths are excluded. They can't form standing waves between the plates. This creates a difference in vacuum energy, more quantum fluctuations outside the plates than between them. This difference in energy creates a pressure, a force pushing the plates together. This was predicted by theory in 1948. It was first measured by Marcus Sparnay in 1958. Later experiments measured it with increasing precision with better apparatus. Better control of systematic errors. The force is tiny, utterly negligible for everyday purposes, but it is real, it is measurable. It matches the theoretical predictions to high precision. It is a force created by the vacuum, by the quantum fluctuations of empty space. The second piece of evidence is called the Lamb shift. It's named after American physicist Willis Lamb, who discovered it experimentally in 1947. Electrons in atoms occupy specific energy levels. Discrete allowed states with specific energies. This is basic quantum mechanics. The energy levels can be calculated from the Schrödinger equation. The calculations are extremely precise. They match experiments to many decimal places. But when you measure very carefully with spectroscopy of extraordinary precision, you find that some energy levels are slightly shifted from their predicted values. The shift is tiny, a fraction of a percent. But it's definitely there. The shift is not caused by other electrons. Not by nuclear effects, not by relativistic corrections. Those are all accounted for in the theory. The shift is caused by the interaction between the electron and the fluctuating electromagnetic field of the vacuum. The vacuum is not empty. The electromagnetic field is fluctuating, even in its ground state. Those fluctuations affect the electron. They push on it. They perturb its energy levels. They cause the Lamb shift. This effect was discovered experimentally in 1947. Willis Lamb measured it precisely using microwave spectroscopy. He won the Nobel Prize for this discovery in 1955. The effect has been measured countless times since then with increasing precision, using different atoms, different techniques. Always the result matches the theoretical predictions. The predictions that include the effects of vacuum fluctuations. The vacuum is doing something. It is interacting with matter. It is contributing to physical processes. It has measurable effects. This is not empty space. This is structured space, active space, a space filled with quantum fields in their lowest energy state, fluctuating at the quantum level, incapable of being completely turned off. Let's push the concept further. What if you could remove the fields entirely? What if you could take a region of space and strip away the electromagnetic field, the electron field, every quantum field, everything? What would be left? We don't know. Honestly, we don't know. No experiment can do this. No theory fully describes what that would mean. Because fields are not optional additions to space. They're not decorations. They're not extras. They are what space is when you describe it correctly with our best physical theories. Space, in modern physics, is not a blank stage, not an empty container waiting to be filled. It's a configuration of quantum fields, a set of relationships, a structure with properties and dynamics. Even when that structure is in its lowest energy state, it is still structure, still something, not nothing. But there's something stranger still. The vacuum we observe, the one with all these quantum fields in their ground state, may not be the only possible vacuum. It may not even be the true lowest energy state of reality. This is where we enter speculative territory. But it's speculation grounded in mathematics. In the equations of quantum field theory, in calculations by reputable physicists, in some theoretical frameworks, particularly in theories that try to unify all the forces, the universe could be sitting in what's called a false vacuum, a metastable state, locally stable, but not the global minimum. Think of it like water above the freezing point. Water at 1 degree Celsius is liquid, stable. It can remain liquid indefinitely under the right conditions, but it's not in its lowest energy state. Ice is lower energy at that temperature. Given the right conditions, a disturbance, a nucleation point, a speck of dust, the water will freeze. It will transition to the lower energy state. If our vacuum is a false vacuum, then somewhere, somehow, at some point, a region of space could quantum tunnel to a lower energy vacuum state. A bubble of true vacuum would form, and it would expand. The bubble would expand at the speed of light. Nothing could outrun it, nothing could escape. The bubble wall would be a boundary between two different vacuum states, two different configurations of the quantum fields to different types of physics. Everything the bubble touched would be restructured, reconfigured, rebuilt according to different physical laws, different particle masses, different force strengths, different fundamental constants. The atoms in your body would not be stable in that new vacuum. The electron mass might be different. The strength of the electromagnetic force might be different. Chemistry would not work the same way. Nuclear processes would be altered. Matter as we know it could not exist. We would not survive it. Nothing would survive it. No warning, no escape, no time to react. The bubble expands at light speed. You wouldn't see it coming. Now, this is not a prediction. I want to be clear about that. This is not a warning about an imminent disaster. This is a possibility allowed by some theoretical frameworks, a feature of certain equations, a scenario that physicists have calculated. Whether our vacuum is actually false or not, we don't know. The calculations are difficult. The uncertainties are large. It might be stable. It might be metastable. We can't tell yet with certainty. But the point is this: the vacuum is not inert. It's not passive. It has properties. It has energy density. It has stability conditions. It is a physical thing with physical consequences. Not an absence, not a void, not nothing. And that means emptiness in the classical sense does not exist. There is no such thing as a region of space with nothing in it, because space is never nothing. Let's return to where we started, that image of deep space, darkness, stars scattered across the apparent void. Now you know what you're actually looking at. You're looking at the electromagnetic field in its ground state, present at every point, fluctuating quantum mechanically, capable of carrying light waves. You're looking at electron fields, quark fields, neutrino fields, all in their lowest energy configurations, present, real, capable of creating particles when sufficiently excited. You're looking at the Higgs field, responsible for giving particles their mass, pervading all of space, interacting with everything. You're looking at quantum fluctuations, too small and too fast to see directly, but present at every point, causing measurable effects like the Casimir force and the Lamb shift. You're looking at structure, not the absence of things, but the presence of fields. The fabric of reality itself. This fundamentally changes how we think about the universe. Space is not a passive background, not a container that sits there waiting to be filled. Space is an active participant in physical processes. It carries energy. It has properties. It fluctuates. It responds to the presence of matter and energy. When a charged particle moves, it disturbs the electromagnetic field around it. The field pushes back. That interaction is what we call electromagnetic force. When a massive object sits in space, it curves the gravitational field. That curvature is what we perceive as gravity. Nearby objects follow geodesics in the curved field. When a star explodes in a supernova, it sends ripples through these fields, light waves. Electromagnetic disturbances propagating at the speed of light, neutrinos, particles streaming outward at nearly the speed of light. Excitations in the neutrino fields, gravitational waves. Distortions in spacetime itself, propagating outward, stretching and squeezing space as they pass. All of these are disturbances in the field structure of space. Space is not the empty stage where these things happen. Space is what carries these disturbances. What transmits them? What makes them possible? And when cosmologists study the cosmic microwave background, they're seeing something profound. They're seeing the signature of quantum fluctuations from the very early universe. Tiny variations in the density of matter and energy. Temperature differences of 1 part in 100,000. These variations started as quantum fluctuations, random, irreducible, a consequence of the uncertainty principle operating in the first fraction of a second after the Big Bang. The exponential expansion of the universe, cosmic inflation, amplified these fluctuations, stretched them from quantum scales to cosmic scales. Microscopic variations became variations spanning thousands of light years. Those tiny variations became density differences. Density differences created gravitational attraction. Regions of higher density pulled in more matter. They collapsed, they formed structures. First, clouds of gas, then the first stars. Then the first galaxies, every galaxy in the observable universe. Every star, every planet, every atom in your body. All of it traces back to quantum fluctuations in the vacuum of the early universe. The vacuum is not nothing. It is the foundation of everything. So, what do we take from all this? What does it mean that space is not empty? What are the implications? First, our everyday language has completely failed us. We use the word empty to describe space, but empty means without content. Without substance, without anything at all. Space has content, quantum fields, structure, properties, energy density, pressure. We should stop calling it empty. We need better language. More accurate language that reflects what we actually know. The vacuum is not vacant. It's structured. It's dynamic. It's active. It's filled with quantum fields. Second, the universe is far stranger than our everyday experience suggests. We built our intuition on macroscopic objects. Tables and chairs, rocks and trees, objects in space. Gaps between objects. We assumed the gaps were simple. Just absence, just nothing, but at the fundamental level, there are no gaps. Only fields, only structure, only continuous, pervasive physical reality. Matter is not fundamental. Fields are fundamental. Matter is what happens when fields are highly excited. Third, nothingness is unstable. True absolute nothingness, if it could exist, would be profoundly unstable. Quantum mechanics does not allow it. The uncertainty principle does not allow it. The vacuum must have quantum fluctuations. Fluctuations appear spontaneously. Fields exist everywhere. Structure emerges naturally. Somethingness is the natural state. Nothingness is the aberration, the impossibility. This completely inverts our intuition. We thought nothing was simple and something was complex. We thought nothing was the default and something required explanation. But the physics suggests the opposite. Something is natural and inevitable. Nothing is impossible. Fourth, this is not metaphysics. This is not philosophy. This is not speculation. This is physics, experimental physics. Observational science. The Casimir effect is real. It has been measured in laboratories around the world. The Lamb shift is real. It has been measured countless times with extraordinary precision. Quantum fluctuations are real. They leave observable signatures in particle physics, in atomic physics, in cosmology. The vacuum has properties. It has energy density. It has pressure. It interacts with particles. It affects their behavior. It contributes to physical processes. These are experimental facts, not theoretical speculations, not mathematical abstractions, not philosophical musings. And that leads to the truly unsettling conclusion. Even in the darkest, most remote region of the cosmos, where no star has ever shone, where no particle has ever traveled, where matter has never been, something is happening. Quantum fields are there, they're fluctuating. They're real, they're present, they're active. The vacuum is there, structured, dynamic, capable of physical effects, capable of creating particles given enough energy. Reality does not stop at the boundaries of matter. It doesn't need matter to exist. It fills the gaps. It occupies the void. It is continuous, pervasive, unbroken, universal. There is no place in the universe that is truly empty. No location that contains absolutely nothing. No point that is blank. No region that is void. Everywhere you look, everywhere you could possibly go, everywhere in the observable universe, quantum fields are there. Structure is there. Reality is there. Space itself is something. It's not nothing pretending to be something. It's not absence with a fancy name. It's genuine physical reality, substantial, structured, dynamic, real, and when you look up at the night sky, when you gaze out at the darkness between the stars, you're not looking at emptiness. You're not looking at void. You're not looking at nothing. You're looking at the quantum field structure of space-time, fields extending through every point, fluctuating at every instant, making reality possible, providing the foundation for existence itself. You're looking at the substrate of the universe, the fabric of reality, the foundation of everything that exists. Empty space is a myth, a misconception, an artifact of limited language and incomplete intuition. The vacuum is reality, the deepest, most fundamental layer of physical existence. Space is not empty. It has never been empty, and it never will be.